record. So it's recording now. Okay, thanks a lot. Okay, so the thing that I want to say, no estimated date. From where did you order? Vigilant and no estimated date. Wow. You know, I ordered something from Apple 5 days ago, and they keep postponing the shipping. They said, you know, first of all, I will receive it today. Then, you know, they changed their mind to 4th. Then, you know, 11th, and they end up being gonna be shipped and, you know, sending to me by like 15th. And I'm not sure whether that they're gonna postpone or not. I know there is a problem based on this COVID-19 problem, you know. But at least, you know, the other people in your team, they have a board, right? One person at the board. That's not enough. That's okay. I mean, you already have Vivado on the software. You will run the test bench, and then, you know, one of you will just deploy until you will get the board, okay? Anyway, so back to the lecture. So, it is 300. Zoom. And then I want to have ability. And we are 3300, right? So by the way, you guys understood from last time that, you know, we have like a regular lecture. Did you understand the trick of the critical path, right? I just want to be sure everybody understand the critical path.
Yes.
Yes.
If you know, don't be afraid, you know, if is there any problem, just stop and say, hey, I don't understand this, I will repeat. So I just want to be sure everybody fully understand this, because, you know, there is a part of this course will be about timing. And the timing is based on the critical paths. So, you know, normally, you know, I bring in the exam 2 questions about the timing, and a lot of people actually have a problem with the timing. So I want to be 100% sure, you know, everybody understand the critical path? Is it clear?
Yes.
If
I mean, just to put it simply, it's the path that takes the longest.
Exactly. The longest one between the input and output. You're right. Michael, Khaled, Ashley, Eduardo, I'm sorry, the rest of the people, is it clear?
Can you summarize how you calculated it again?
Once again?
Can you summarize how you calculated it again?
Sure. So do you remember I gave an example last time about the 1-bit full adder, right? In a 1-bit full adder, we build a circuit like what? Do you remember? We have the XOR gates here, like this. This is the equation in the Boolean algebra, right? And there's a bunch of the ending with ORing, which is bringing me the carry out. This is from the 2300 knowledge, if you remember. Then we are building the circuit, and the circuit in front of you with these different colors. Okay? As you know, as Mario and, you know, Michael and, you know, Eduardo, you know, we're talking before, you know, what does the critical path mean? It means that, you know, the longest path between the input and output. From your point of view, where is the input? Here's the input, right? Where is the output? The sum and the carry out. You agree? Now, I'm starting to look into the timing response of every single gate in front of me. But I give an assumption in the lecture. What is the assumption? This circuit is purely built using 2 input NAND gates. And I give the response time of the NAND gate by 1 nanosecond. What does it mean, response time? It means that, you know, if I have an NAND gate and I put the 2 inputs of the NAND gate, how much time for the output to be processed of the NAND gate? That's called response time. So I said the response time here is 1 nanosecond. So what I did, I came and I say, okay, I have here AND and OR and XOR, right? But I just want to use NAND. So in that case, I have to remember from the 2300, how can I convert AND to NAND? How can I convert XOR to NAND? How can I convert OR to NAND?
Is the timing of the NAND gate gonna be given in each individual problem?
Of course, I mean, I'm not saying NAND, maybe I can make something else.
Yeah.
You know, normally in the technology, people use two things. Okay, Elvis? They use NAND or NOR.
Yeah.
Technology-wise, like, you know, the watch I have here, the iWatch, right? The processor based on NAND gate. Some circuits based on the NOR gate. There is nothing actually in the reality it's called AND gate. There is nothing called OR gate. It's just a logic, you know, we are writing by our hand.
Yeah.
But in reality, based on the NAND and NOR. And I'm going to tell you a story. You might actually heard about it if you are taking VLSI, but I don't think you're taking VLSI, all right? You're taking VLSI? Have you guys heard about something called VLSI course?
Yeah, but I'm not taking it.
Okay. Yes. So Christian, you know the VLSI, right? So how it works, the gates we are taking, it's not gates anymore, it's transistors. So for instance, you know, the NOT gate like this is a NOT gate, right? NOT gate, how it does look like, it's a basically transistor based on something is called CMOS, complementary metal oxide silicon, which is symbol-wise a transistor transferring holes connected to transistors transferring electrons. And then those guys connected to each other like this. And here is the ground, while here is the VCC, and here is the input, and here is the output. This is completely a NOT gate. This is a NOT gate. Then, if I look more into the other gates, I will find that I have NAND or NOR. I don't have AND. So for instance, one of them like this, if I would like to build using the transistor CMOS technology, 2-input NAND gate, how it does look like, it's gonna look like this. No, I'm sorry, I have to clean it because it's a reversible thing. So if I make it serialized like this, the other one, it has to be parallel. So what in front of you is what? NAND. This is 2-input NAND gate. NOR gate reverse. So basically NOR is gonna be like this. If I want to build out of this AND gate or OR gate, then I have to what? Make it to stages. Do you remember? So you have to put NOT gate of the NOR gate, it will be OR gate. NOT gate of the NAND gate, it will be AND gate. So that's why people actually build the rest of the stuff from the NAND and NOR. That makes sense? And the libraries, I'm not sure how many of you are, you know, following the press conference of the Intel, for instance, when every year they come and announce a new processor. You guys follow stuff like that?
Yeah.
So while they're announcing, they will come and say that, you know, we build the processor X with 14 nanometer technology, or, you know, 7 nanometer technology. You know what is this?
How big the transistor is?
The size of the transistor. So that means, you know, how many transistors on the chip it will be occupied. How many transistors on the chip will be there. So of course, when I will make the transistor smaller, a lot of what a lot of transistors can be what fit into one chip. Okay? Then, you know, this symbol thing of the circle, that means, you know, I'm pushing, yes, Moore's law is a different thing. Moore's law say that, you know, that the processors will come twice fast every year on the fabrication process. But then, you know, because, you know, the transistor getting smaller and smaller, the number actually went down. Exactly. So in that case, actually, what happened, Moore's law is almost gone. It's bye-bye. That was in 60s. Now, you know, we are losing it. We are towards end of the Moore's law. That's actually this course I'm going to be covering in the 5850, which is the graduate class I teach. Okay, that's for the master degree. Anyway, I don't put too much in the top of your head, but, you know, in general, people trying to run away with the semiconductor and trying to use something else. From the physics perspective, there is something that's called silicon carbide. There is fiber optics. There is quantum, using particles and photons instead of using electrons. But, you know, too much, you know, forget about it. Just like, you know, think about it from the way that, you know, I told you something for fun. Okay? Now, yes.
Professor, can you go back to the schematic?
Here?
No, the one up of it, yeah. Above it. So the one on top is the NOT gate, and the one on the bottom is, sorry, the one on top is an AND, and the one on the bottom is NOR.
One of them is NAND, one of them is NOR. I don't remember very well, but I think this is actually the, 1 second. If you open one, it's still the other one there. No, this is the NOR.
Oh, this is NOR. Oh, okay.
You know, because, you know, NAND, both of them has to be there to make it one. So if this one opened, the circuit will be bye-bye. There is no circuit, right?
Yeah.
But there, you know, or if any of them there, the circuit will still pass to the ground. So that's why this is NOR and this is NAND.
Yeah, okay. In general, in industry, is there something between NAND and NOR that makes like NAND better? Because I noticed that they use NAND more than NOR.
Yes, the NAND in terms of size is smaller. So it does take less power than NOR. That's why people prefer NAND for decreasing the power. So
is there any advantage that NOR brings?
NOR speed. NOR speedy. It's a little bit faster than NAND. But, you know, NAND is following this LVLP. It's a concept in the industry. It's called low voltage, low power. So before the circuit was powered up with 3 volts, then, you know, 1.5 volts, right? Then 1 volt. Now what is this 3 volt, 1.5 volt, and all of these guys? Those guys is based on the gates open and close on the transistor. You know, take this information like extra information, okay? There is no part of the exam about this, okay? So normally how it works, you know, if you have a transistor, right? Let's say this is our transistor, right? So the transistor in general is a bunch of what diodes? Like gates open and close, right? So, you know, this gate is allowing the flow to go from the source to the drain. Like, you know, I'm pushing electrons and, you know, getting on the other side, okay? So who is actually gonna control the traffic? The gate, right? So there is something that's called VGS, which is the opening gate. This is the G and this is the S. So the voltage here, it's sometimes called 0.3 volt. So this is the lowest voltage can open the gate. It is possible to design an OR gate using transistors. No, it's of course, you know, because, you know, you are using what? Negation here, right? So you're using this. So it's not difficult. It's what you're gonna do. You're gonna take this part, which is NOT gate, and you connect it to the NOR gate here, the output of the NOR gate. So that's gonna be OR gate. You understand what I'm saying, Mario?
So why? So if everything's possible to create using transistors, these NOR and NAND gates are just preferred simply because the efficiency of the design, or
those are the basic.
Those are the basics.
Yeah, I mean, have you noticed something? What is the smallest circuit ever you have here? This one, right? I'm sorry, it went somewhere. Excuse me. Here, right? This is what NOT gate, right?
Yeah.
The second is what? These two guys, right?
Mhm.
So this one, you know, here is the output is giving me NOR gate, right? If I want to OR gate, as you said, what should I do? I have to go ahead and take extension of this and connect it to what? Like this, right? I'll connect it to this one. So how many transistors you gonna have? Look, 1, 2, 3, 4. Those 4, it will have 2 more. So 6 transistors will be used to build the OR gate.
Oh, so it's more like the NOR NAND
You keep adding
are the simplest
exactly.
gates we can create using transistors.
Exactly.
Anything else gets more complicated. Okay.
Completely, exactly. Let me tell you another story. Why I'm bothering you with this, even we are in Verilog. I have a news for you. Every single thing in industry using Hadoop description language, but you know what is called here is called layout. Is the last stage after you write the Verilog. So if you write Verilog, and then you know your intention is to put it on FPGA board, you're gonna use Vivado, or you're gonna use something else. It's called Quartus. So you know what's Quartus, right? So I have here a bunch of FPGA in my office. It's based on Altera technology. Altera got acquired by Intel a couple of years ago for $16.7 billion. So now Altera is part of Intel. You know what I mean? So their software is similar like Vivado, but it's different names of files and so on, and different GUI, graphical user interface. But end of the day, the same philosophy. You write a code, you know, the code will go into the tool will digest it into a bit stream, you map it on the board, it will work as an FPGA. But then the same code you are writing, if it's generic enough, that means you're not using a specific device inside the FPGA, can be translated using Synopsys tool or Cadence tool to be what? ASIC. To be bunch of NAND gate and NOR gate. And that will be deployed on the semiconductor. That's basically what I said in the first lecture, if you remember. So now you understand why Verilog is important. Because if you understand Verilog, you're not gonna even program FPGA. You're gonna program FPGA. You're gonna program ASIC. You're gonna write verification for FPGA. You're gonna write verification for ASIC. Look how many jobs you can find under the title of the Hadoop description language. Make sense?
Yes, completely.
It is very important. That's why, you know, I'm actually, my expertise in hardware was cryptography. I mean, I work with security, but even I have a course in spring, it will be about using the reconfigurable computing FPGA with crypto primitives, like encryption, decryptions, and stuff like that. So of course you have to know what is Verilog is, okay? Anyway, so critical path is very important, Eduardo. Elvis, based on the critical path question you asked me, it is very important. If you understand critical path, then you will be able to understand the timing report. I will show it to you in Vivado. Then you will be able to decide what is the maximum frequency you have. Because, you know, let's say that you build a circuit, and this circuit is a bunch of combinational circuit with sequential circuit, right? Then you came and say, I would like to operate this circuit on 300 megahertz. But then the timing report will come and tell you violation. You cannot run in 300 megahertz. How you will know that, you know, what is the best and optimum maximum frequency you will reach? Based on the critical path. Okay? Anyway, if you guys remember last time, you know, while I was with you, I talked about how to make an instantiation. So you guys, do you have any problem with instantiation? I'm taking my time in the beginning of the Verilog because this is like, you know, I'm building a big palace at the end of the day. So, you know, if the basics are not there, we're gonna suffer the rest of the course. You know what I mean? So basically, you know, let's start again. My question, does anybody have any problem with instantiation?
Just to make sure, instantiation is what we were doing on Vivado last time. I mean, maybe like a quick recap would be good.
Yeah, yes, that's perfectly fine. The question, do you remember when I told you about the full adder? So
Yeah.
let me open the full. Let me switch my screen into the screen of Vivado, and we can talk about it. 1 second. Can you see Vivado?
Yes.
So see recent projects. I clicked on one of them, right? Just drink some water. Look, do you remember when we built in the beginning 1 bit full adder? And we built it using a structure. You remember how I told you there's 3 different modeling of describing the relation between input and output, which is called transfer function. If anybody actually interested in control circuit or control system, I'm sorry. So the way that we use in the structure modeling, that means, I'm gonna use bunch of gates, right? And this is basically what we have here, right? Here is XOR, XOR, and OR, and all these things. Make sense?
So that's all instantiation is.
Huh?
That's what instantiation is. That's it.
Yes. No. That's not an instantiation. Instantiation means that this block I'm gonna replicate it multiple times in a different level. Because how we build the stuff. If you are a really fan of Lego set, right? What you do, you bring some bricks, you put it together, you build something, right? And then you bring another bricks and you put it together and you build something else, right? Then you will bring them together and you put something in the top of them. They will build another hierarchy, right? Then you will take them in a bigger picture up to the end of the figure, right? So that's the same thing. I build 1 bit full adder in front of you, right? And I call it FA. Right? Then I came and I made a new file, and this file I call it what? FA 2-bit. When I say 2-bit, that means I have to have 2 1-bit full adder, right? I don't want to write it again. So what should I do? I will instantiate it.
Yeah, basically it's just like
It's calling function, like Mario said. Yes, it's like C. You have subroutine. So now look, the name of the one, it was FA. Look at my cursor, right? You will sign what? Unit underscore 1, and then you already have the column and then FA, right? Why? Because the name there, it was FA.v, right? There is FA.v, but I call it FA, but I give it a name so I can repeat it multiple times. So now see, I call it unit 1, I call it unit 2. And then I start passing wires between of them, right? Because if you remember how the 2-bit full adder, based on the rebel carry adders, the carry out of the first full adders will go to be carry in of the second full adder, and so on. Just from the 2300. That's not very long, okay? So anyway, once I did this and it's completely connected correct, I will look into my left side and I will find that the 2 units came in a hierarchy under the 2-bit. That makes sense? Then I have here the test bench, and we talked about the test bench, right? So if I click here on the test bench, normally test bench also you are instantiating, right? Because you are instantiating the module you would like to test. So I instantiated here, and I wrapped it up with what? Register and wire. Mario corrected me last time when I made it the input wires and the output register. And he was right. Why? Because the input should be registered. End of the day, I'm gonna feed input. I'm gonna assume that, I have like a source or power supply with me and I keep pushing inside the input with something. Like what you are doing on the breadboard. Then, the wire is something coming out of the module, which I would like to hang it and see it. I see it by what? Waveform. How can I see it by waveform? I click here the initializations of the wires, of the registers of inputs. And if I click and run simulation like this, automatically it will give me a waveform describing the input and what is the output based on this input of the design. And then I know the functionality. I know that it's a 2-bit full adder. So basically I know it's adding. So I expect that, if I add 0 plus 2 plus 1 to be 3, it is 3 and there is no carry out. I expect that, 3 plus 1 is 4. 4 plus 1, 5. But, 5 is 1, 0, 1. But I have 2 bits. So that means the bit number 3 is out. So that means the output I'm expecting is going to be what? 1 with carry out. What I'm doing in front of you, or basically this bench, you have to think about all possible corner cases. What does corner cases mean? Corner cases mean the tricks that, normal people will not check or see. For instance, if I have a counter counting from 0 to 255, if I ask you a question, give me an example of corner case of this counter. Somebody can give me a corner case. Any idea? If you have a counter, and this counter counting from 0 to 255, what possible corner case I would like to check?
Would it be going from 20 to
exactly one of them that I should be is exactly Ashley is right. I have to be sure that when I have to start from 0 and I have to close by 255. The second, I have to be sure that 255 it will come after that 0. That makes sense. There is no 256 as Edgar mentioned, and and Alpha said. So you understand what I'm saying? So that's called corner cases. So you have to be tricky enough to fully understand and digest the specification, then you will be able to process. That makes sense? Like the adder, for instance. Let me say something. Adder, the adder 2-bit, right? So if I add 2-bit to 2-bit, so the output, it should be what? In 2-bit, 3-bit. Normally, that's what we say, right? So think about it from this perspective. I added 2-bit, that means, 3 to 3. That's the maximum. 2-bit, it can give me here 3 maximum, 3-bit maximum, right? So I have to add 3 to 3 to be what? 6. So I have to be sure the output will be 6. Make sense? Okay, anyway, I'll switch back to the notes. And then, we will move forward. And after that, I will go into the parameterized, how can you use the parameterized, and we'll make a couple of examples. So,
Professor?
Yes, sir.
I had a quick question. So when the code is synthesized, is it interpreted line by line or compiled all at once?
It's a parallel language. That means it takes stuff in parallel. It doesn't go like C.
Okay.
So you understand what I'm saying? So for instance, in front, do you remember that this bench? Let me turn it back to this bench 1 second. This bench is sequential, kind of. I'll give you an example. Look here, right? Here in front of you, like FA, right? This code is gonna be parallel programmed. That means, it will take AND here, take OR here, it take all of them together. And actually, when you are running synthesis, let me show you. Synthesis setting. Scheiße. Anyway. Look, here is also telling you what resource is going to be used. Like -1, that means use all of them. But not important now. I want to show you. There is a trick saying that, when you are running your code, how many core on your computer you would like to process. Okay? So that means, let's say that my computer has 8 cores. I'm just giving an example. So that means, if I want to make the synthesis process to run fast, I will assign the job to all of the 8 cores in my computer. Then the synthesis process will be faster because it's a parallel language. Okay? Anyway, back to the...
Wait, Professor, I had 2 more questions.
Sure, go ahead.
Could I have multiple modules within the same Verilog file?
Yes, you can do that. Sure, look. Normally, this is organizational thing, which basically I want to teach you this. I don't think that not many people will do that, but for me, because I really like to follow the industry standard. If you guys go into the internet, okay, and search for the Google code guidance or the Intel code guidance, So they have like a book of the code guidance. Like you already have a project, right? This project, it has a full adder, right? So every single signal or wire or register inside that thing, you can call it what? Full adder, underscore, the name of the block, underscore, the name of the wire. So you are following a certain style of writing code, okay? That's one thing. The second, you said, if you can have a multiple module. Yes, this is a multiple module in front of you. Even they are identical, but they are multiple modules, right? Second thing, the biggest file, we call, while you finish the whole design, we call it top.v. So basically, instead of making it full underscore 2-bit, you're actually gonna call it top.v. This one, see, fa underscore 2bit.v, you call it top.v because it's the top module. Under the top module, the submodules. Submodule in our case here is 1-bit full adder. Make sense?
Yeah, that makes sense. Another thing I was wondering is if we had a data race condition,
yes,
where they're both like either in the same stack or trying to reach the same register, how would the program handle that?
The program in that case will actually pick randomly, which is not good. So basically, we have to avoid the risk condition. That's a very good question. And actually, risk condition, you will find it in the document somewhere. I already talked about. Do you remember the blocking, non-blocking I mentioned somewhere in the documents? If not, I will go through it. Don't worry. I'm going to go through everything from scratch. So blocking, non-blocking, it's a way of avoiding the risk condition. Okay?
Okay, thank you.
Any other question, guys? Anyway, now back to the... It's really hot here. I don't know why. They turned off the AC in the university. Everybody can see my screen?
Yes.
Super. So the full adder I already covered using the Vivado in front of you, right? Now I want to talk about something that's called parameter. So what is parameter? Let me tell you a story about parameter. So imagine that, I build my circuit for the 2-bit full adder, right? Then, for either or other, I came in one assignment and I told you, can you please build a 16-bit full adder? So you don't need to start a new project. And from the new project, you will be able to generate a new 16-bit full adder. What you can do, you can from the beginning make a parameters or parameterized full adder, and you put the value inside the module while you are instantiating. Example, let's say that for instance, I want it to be 16. Then, I will put 16 in a specific designated area. Then, it will automatically expanding the whole entire design to be 16-bit. Then one day I would say, no, I don't care that much about 16. I want it to be 8. So I will go in the same area. I remove 16s. I put 8. Then everything will be voila 8. That's it.
Professor, so in Verilog language, can we do the same thing with C? Like, for example, integer x, and then we use x like in various places in the code?
Here's the thing what I'm going to talk about now. So there is 2 things. One is called parameters. One is called local parameter. There is another thing is called variable, global variable, but this is in VHDL, not in Verilog. Anyway, so system Verilog, they have it. So parameter, listen to this carefully. Imagine the following. I have a module, right? And this module inside it, I decided the local parameter to be 16. 16, right? Then I came and I take this module and I instantiate it in another module. And I instead wrote 8. Guess what will happen? Error. Why? Because the local parameter cannot be overwritten. Local parameter cannot be overwritten. Okay. What about parameter? Imagine that I build a unit and I call it full adder 16. And it has a parameter inside and I make it 16. But then in another module, I want it to be 8-bit, not 16. So I will instantiate it and I will remove 16 there, not in the original one, into the instantiated version. And I will put 8 there. It will automatically understand it's 8. So parameter is more dynamic than local parameter, which is something what you're saying. You already have a global pointer while you have a local pointer. You know, something can go into the subroutine and other can go between the subroutines. So parameters, you can overwrite it. Local parameter, you cannot overwrite it. Make sense? Also, I mentioned in the beginning about the register where the supply 0, supply 1. Do you remember this? And the tri-state and all of these guys. So this is very important. Let's say that I would like to define a bus. What does bus in circuit mean? It means that a bunch of wires into a certain name, a certain category. So the one in front of you is rig, size -1, color 0, data B. It means that, you know, I have two buses. One is called data and one is called data B. Each one, the size of it is what? Size -1 to 0. So which is mean size, basically. Make sense? 1 second, because, you know, my tablets, because I put it in a low power mode. Anyway, that makes sense? Now, declaration. How can you, you know, okay, we know parameter, we know the local parameter, but how can we declare it into the module? So here's the declaration. Can you see the declaration? There is multiple versions of Verilog. One of them is the popular one, which is called 2001. In the 2001, here you already have the module name, and then you follow by the parameters. And then, you know, inside you will call the size multiple times. I need to give an example about this, but before the example, I will go into the representation of the numeric numbers. So while we're representing, I did before, while I was coding in front of you for fun, that, you know, you can code using binary. You can use hexa. You can use what's called octal. You can use signed. You can use unsigned. You can do whatever you want. Example for this, decimal. So imagine that I have 16-bit. I would like to represent the value of them in decimal. So what should I do? I would just say that they are 16. And then here, semicolon, comma. And then, you know, you already have here, and then you already have here the sign of decimal. And you put the value in a decimal form. Then hexa, for instance. Hexa, and I have 8-bit. So I would just say I have 8-bit, but I would like to represent them in hexa. Hexa, that means 2 digits, because 4, 4, 8, right? Then binary, I know binary for sure. How many binary I have? I write it here. So I have to write here like this. Let's say 3 bits. So comma, B, and then 0, 1, 0. If I want to make it wide open without putting a designated number of bits, I can make it open like that. So I don't put number here. But automatically, it will be considered maximum 32 bits, as you can see in front of you. Octal, same thing. Yeah. Also hexagon, same thing. Now I want to make what? I want to make it hexa unsigned. Somebody can tell me what is the difference between signed and unsigned?
The unsigned can fit one more because there's no bit to determine if it's negative or positive.
This is unsigned or signed?
It's the unsigned.
And where is the location of it?
The first one on the left.
You mean the most significant bit? Let me actually, you know, we should have a common terminology here. There is one is called MSB. There is one is called LSB. So if you have a certain register like this, right? The one on the left, we call it MSB. The one on the right, we call it LSB. So most significant bit, least significant bit. So the most significant bit is the bit designed for the sign. If it's 0, that means the rest of the values here will be representing positive value. If it's 1, that will be representing a negative value. Except 0, 0, you know, it has its own case. There is nothing called positive 0, negative 0. No, but there is something I have, it's called little 0 and big 0. Do you guys know what is the difference between big 0 and little 0?
A big 0 is if you get a 0 on an exam or something?
No, if you make something wrong in the fundamental thing. That means if you came in like, you know, KCL And instead KVL, I'm saying instead of you add all the voltages in the whole loop, and you said the voltage in one node coming in is equal to the voltage from coming out. That's called big zero, because you don't know what is the difference between KCL KVL. How are you gonna pass circuit? That's called big zero.
Yeah, maybe you should change the major.
Yeah. Okay. No. I mean, mistakes happen, but I'm just giving an example. Little zero. Okay, you added two numbers wrong. Okay, partial credit will work, and then everything will be fine. I have a question for you guys. Why they put the sign of the value in the most significant bit? Is there any reason?
Sorry, can you say that again?
Is there any reason for them to design the most significant bit to be holding the sign? Why is not the least significant bit? Why is not the second bit of the register?
Because it's the last one to change.
What?
Is it because it's the last one to change, or maybe it's like the first one to be read by the computer?
No, because it's a standard. I mean, I cannot change it as much as I want. One day I designed a circuit while I was a student, and I came with a report written in 15 pages saying that, I designed my circuit using the most significant bit to be the middle bit. And the professor was like, what? And I started going on the whole entire whiteboard, writing to him all the things. And he was looking to me like, wow, you decrease number of resources. It's just a way of optimization. But, is it possible for you to use it in normal life? Of course not, because, we are following standard. Like, I decided that my minute is 70 seconds, but the whole entire world, their minute is 60 seconds. Could you try again? Yeah, Siri talks to me all the time, She said, I didn't get that. See, she got like, confused that I told her, the minute is 70 seconds. Okay, so it's up to you. But then, people have to convert to your system, and it's gonna be really painful, right? So that's why people go in the standard. Make sense? Anyway, there's some illegal things happen in numbers, and I want you guys to know it for sure, right? So if somebody, for instance, would like to write 3 in 8 bits in decimal with gonna be negative value. So how he gonna do it? Best way to do it, to put the negative, and you just say that they are 8-bit, comma, and I want it in decimal to be 3. What else? Can you use assign values for the parameters? Like, could you assign parameters? But don't forget, if you make a parameter with negative, there is no negative in the parameter. The parameters has to be positive. You know what I mean, Ashley? So yeah, normally, there is no negative parameter, because, you don't have that much. You are representing facts here, right? How many units? You cannot say, no, I don't have units, basically, and I need this unit. But it's very good, we can do it in a quantum, because what you can do, you can make a scheduling. You say that, I will need those guys. When they will come, I will start working. You know what I mean? Like you determine your own resources, basically, before you will get them. Anyway, so the illegal one, like I would like to write -2 in 4-bit in decimal, something like we have here in illegal, right? I put here 4 decimal, and then I put -2. This is not correct. Syntax wrong. It will give me an error on the Vivado. Since, our exams and everything here is gonna be based on the internet, you guys at home, I'm not gonna give you the midterm or the finals or the quizzes like in the whole entire hour, and then, I will take it back from you. I can give it to you in a day or so. So you have the time to go in Vivado and test your code before you write it. That makes sense? So you open Vivado, check whether that, you are saying something correct or not, and you put it on the document, write it, and then, you will load it in a Redis code. That would be very appreciated. You can also put waveform. That's very appreciated. So that show that, you are interested in the subject, and you know how to use the tools of the subject. This is what exactly I want from you. I'm not going here in a race to give you something completely difficult and I come and say, oh, he doesn't know how to solve it. The most important thing for me actually to all of you to fully understand what I'm saying. Now, if a person really like to be organized on representing something, a value, like that value is really huge, right? Let's say in an example we have a 32-bit wide register, and I would like to represent 8 characters, which is basically 8 digits of the hexadecimals in a very nice way. So what I can do, I can bring them, you know, double digit underscore, double digit underscore, double digit underscore. So to readability, it will be much better. So for readability of the number, you can use the underscore, as you can see. Also, any bits, any wire, any bit or any wires, it doesn't just have 1 and 0. It can have 1, it can have 0, it can have I don't know, or I don't care, right? Again, so any wire can hold 0, any wire can hold 1, any wire it can hold something I don't care. What does it mean? It means that I don't care that much about that wire. It can have 1 or 0. How can I represent it in number x? X's mean I don't care. And we know that from the 2300, right? What about if this wire is floating and it doesn't have anything connected? What does it mean floating? It's not connected to any source of voltage or current. In that case, it's called what? Connected to high impedance, Z. Again, so you already have 0, you have 1, you have X, you have what? Z. You can play with those as much as you can. 1, 0, X, Z. Those are the values you can hold in the registers, in a wire, in a bit representation. So now we fully understand numbers. We understood how actually we can have a problem providing an error in the numbers. How can we make it correct without it gonna be sign assigned as we mentioned. Now arithmetic operation, I'm gonna go through a little bit fast and then I will make the parameter example in front of you later on. We still have a lot of time. So arithmetic operations. So we have a bunch of arithmetic operations. Why arithmetic operation is important? Let me give you an example. I built here in front of you full adder using what? Structure modeling. Those operators for the behavior modeling. So if, for instance, if I go and say, hey guys, I want you guys to build me 2-bit full adder structurally. So you're gonna do it exactly as I showed to you. You build one bit full adder using a bunch of XOR and OR and so on. Then you will replicate it, instantiating in a top file. It's called 2-bit, and that's gonna be 2-bit full adder. But then I came and say, no, what I want a different thing. I want you to do it using the behavior modeling. So instead, you would just say A plus B is equal C. Make sense? A plus B is equal C. A is 2-bit, B is 2-bit, C is 3-bit. Because I know that. I know that for sure, if 2-bit added to 2-bit, so 3 plus 3, maximum value of each of them, the expectation of the output will be 6, which is representing in 3-bit. That's a corner case. So I have positive, which is adding. An example, for instance. So I gave here example for you. Let me make it a little bit bigger so you can look at it. With whatever we learned so far about 0 and 1 and X and Z, look at the table there, right? So AN, it's a name of an input, and the value there is a 5-bit. BN, it's a value represented in a binary, which is 1, 0, representing 2. CN is another value, BN is 10, I'm sorry. CN is representing in the binary form 2-bit, which is 1. DN is representing in 2-bit, the most significant is 0, and the least significant is high impedance. That means it's floating. It's not connected to any source of what? Voltage. Now, if I will make combinational adding between of them, multiplication and so on, let's see what the output expectation will be. So if I add BN to CN, what the output will be. So I'm adding 2 to 1. The output will be 3, as you can see, 1, 1. If I add Bn to itself, what the output will be? If I add An to Dn, what the output will be? So look at this. This is very important. I'm adding Z as impedance to a value I don't know, or I don't care. So that's why it's X. So look at this very careful. It's common logical things. I want you to look to these tables carefully. And I believe I already give you the material last time, so you can look at it as well. Then, you know, if you subtract, for instance, how are we gonna do it, and how gonna be the outputs there? Multiplication, for instance, you know what does multiplication mean, right? So from the 2300, we know that the multiplication means that I'm adding with shifting. How many of you agree about this? How many of you agree about that? You know, multiplication is addition. Exactly. So multiplication is basically addition. Addition with shifting, which is the logical part. That's why you need what? Arithmetic and logical part together. They call it ALU, or arithmetic logic unit, ALU. So your CPU, it has ALU. It has the brain, which is doing the addition and shifting arithmetically. And that's basically what's happened in the human brain. Then the division sign, the modulus. How many of you heard about modulus? How many of you heard about modulus? Yes. So if you have saying that, you know, 7 modulo 4, what is the output will be? 7 modulo 4, what is the output will be? 7 modulo 4. Somebody can tell me.
3.
3, exactly. Because it's a ring. It's a ring modulo. Modulus means you are going in a ring. And the ring 0, 1, 2, 3, 4. Anything out of 4 is gonna be what? Back to be 0, 1, 2, 3, 4, and so on.
Professor, I just have a question about the addition in the first one. So, so for example, AN is decimal, but BN is binary, right? Does it happen where we would add those together or no?
You can add them together. Look at it. You know, this is 10 plus 1, 12, 11. It's fine.
10 plus 5. Oh, sorry. Oh, so BN is 10 decimal.
Yes.
And it's adding.
Added to 1 binary.
So it always gives you if one of them is in decimal, it gives you in decimal. It doesn't give you in binary.
It should be in default. Yes.
Oh, okay.
Okay. Normally, what happens? The compiler back of the compiler will do all of the process. You will not feel it, and default thing is gonna be as a number 10. Basically, one of them decimal, then the whole thing will be decimal. Or you can change it in a wave form. So let me show you in the wave form. Actually, we're gonna stop here. I'm gonna shift back into the thing, and I'm gonna show you something. Okay. Yeah, it's back. Share. Everybody can see. Run simulation again. Here's the value. Then, you know, look at this. Click right. I click right on the name of the signal I call. And it say here what? You want it to different color, you can different color, name. Here, radix. So do you want to present it as what? Do you want to present it as hexadecimal or octal or, you know, ASCII or whatever? Unsigned, sign. Let's say that binary. So look, 0, 0. Added to what? 0, 0 added to 2, right? The output is what? 2 plus 1 here, because the 1 carry in 3. So I can just click here and I say, you know what? I don't like this. So I'm gonna radix here and I say that, you know, make it signed. So it's signed. What happened is 1, 1. It figure out the most significant is what? 1. So it says minus 1. Do you agree? Do you understand what I did?
Yes.
Is it clear?
Yeah.
The rest of the world, and the rest of the course?
Yeah.
Super. Yes. Good. So basically, you know, we play with the thing. It's called reconfigurable, dynamic and reconfigurable. I love the reconfigurability. It shows you how the flexibility you can build the stuff. It's like you already have, you know, this, how to say, the thing that the kids play with in the school, what's called? I forgot. It's like a dough, right? You just like, you know, take it and, you know, shape something, and then, you know, you change the shape, and then you make another thing, and so on. How fast you can do this, the fastest you have in the nation, the Play-Doh. Yes, you're right. The Play-Doh, yes. So thank you, Justin. So, you know, basically the same thing, like, you know, the fastest thing in ever you can have humans. You have the brain is like this, you know, neuron connected to neuron, neuron connected to neuron in no seconds, and I'll come and say, oh, my eyes start looking to you and say, oh, this is Muhammad. While I'm listening to you from my ears and say, oh, you know, Mario's talking to me. While I'm writing by my hand a letter to Michael, and so on, you know what I mean? So that's basically how the reconfigurability in our life. Anyway, back to the slides. Everybody can see again, right? Anyway, so this is one of the tables. You know, I want you to look at it. It's really fun, nothing scary, and so on. Logical. When I say logical, there is something that's called bit operation, and there is something that's called bitwise operation. So what is the difference? One of them, if you have a bus and if you have another bus, right? The bus itself, it has a bunch of wire in both sides, right? If you want to apply a specific process on a specific wire inside the bus, not the whole general rule in the bus, then you're talking about what? Bitwise. That means you're taking bit by bit, bit by bit, bit by bit, bit by bit, you're connecting a new wire bus. So for instance, if I want invert, what does invert from your point of view mean? Not gate. So if you make a not gate, you write knots and then, you know, parentheses and so on, you're using a structure. But, you know, if you are doing this, that means you are moving into the two other models, which is the behavior or the data flow model. So you have the invert, you have the AND gate, you have the OR gate, you have, the OR gates, you have the NAND gate, you have XNOR gate. And look at the XNOR gate. You can put it either way. You can put AND, you can put it XOR followed by NOT gate, or the NOT gate followed by the XOR gate. Okay, same rules. You can look at it for the X and Z and the numbers as well. And this is repeated. Now, this is just an example of the bitwise, right? Imagine that I have input, which is 4 bits. So I have the input 4 bits, right? And this 4 bits input is gonna produce to me 6 bits outputs. One of those is a bunch of applying and an OR. What you can see in front of you, I'm concatenating. Okay, so if you say and an X, it means that every single bit inside the X will be ANDed to each other. Like, you know, bit 0 in X will be ANDed to bit 1 in X, and the output will be ANDed to bit number 2, bit number 2 will be ANDed to bit number 3, and so on and so on and so on. Make sense? Second thing, what in front of you now, in front of us on the screen, is called data flow process or concurrent statement. What's called again? Concurrent statement. Concurrent statement. What does it mean? This is just applied for wire. Again, it's applied for wire, and it's called concurrent statement or data flow. Data flow mean you design a certain wire, and you will come and say you assign value into the wire based on the operation we learned in the above. So for instance, I assign to the bit number 5 in the output to be a combination of ending of whatever in X. I assign to bit number 4 in the output to be the NAND of the whole entire X. I assign bit number 3 to OR all of the bits inside X. I assign bit number 2 to be NOR of all of the input of the X. I assign bit number 1 to be what? XOR of the whole input of X. I assign bit number 0, the output it will be the process of XORing of all the bits Y's of X. Is it clear? So that's a different way than what I showed you in the early stage. That's called data flow or the concurrent statement. That makes sense? Is it clear? Hello? Okay. Now, so I built a module in front of you, and I call it gates 4. That's the name. Now I move into the top folder. So as I told you, Mario, and I told you, Michael, and the rest of you, I said that I like everything to be more how to say, well represented. So in that case, I want to make a top file, and I call it what? Gates 4 underscore top V. So the name of the module is called gates 4 under top, and the file extension is V. Then I decided to package it, to package the design up by saying the input, it will be switches, and the output will be LEDs. This is the way that we're going to represent it on the FPGA, right? Then I will extend wires and instantiate the one here, which is called gates 4, and the instantiation name, it will be called X4. That's what I did. So that's a very good practicing for the instantiation. And because I don't like to, I don't remember the order of the input and output, I put this dot and the name as I did this .x.z, as I mentioned in the early lectures of this course. Majority encoder. Let me tell you a story. I'm a big fan of tricking people. I have a question. Have you ever, guys, think about that the 1-bit full adder can be built using a majority encoder? One of the questions I give it to people in the 2300, maybe a couple of years ago, it was very tricky in a way that people came outside and say, what is this guy talking about? He's given us something completely weird. And I'm gonna share it with you, as I'm gonna invent you something else to trick you. But anyway, so imagine the following. You already have one, Scheiße. What the heck? I added something here, right? Here. Okay. Imagine the following. Let me take off this. Imagine the following. What is the following? I want to build 1-bit full adder using majority encoder with NAND gates low response time. What does it mean? It means the following. Here is 1-bit full adder. I have an input A, I have an input B, and I have a carry in, and I have a B output, and I have a carry out. And that's called 1-bit full adder. I make a truth table, and everybody knows the trick. A, B, C, N, 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 2, 3, 4. And then I have here the sum, and I have carry out. 0, 1, 1, 0, 1, 0, 0, 1. Then 0, 0, 0, 1, 0, 1, 1, 1. Do you agree? Now, Ali said that, Professor Ali said that we need to build it with majority encoder. Where's the majority encoder? So the majority encoder is the carryout. Could you imagine? Because, if you imagine that, I have here extra line, and this line is called majority, the output of the majority encoder. So I'm looking for the majority of the input to be 1. So this one is 0, this one is 0, this one is 0, this one is 1. This one, I just have 1 and I have 2 zeros. So basically 0 is more than 1, so it's going to be here zeros. This one is 1, this one is 1, and this one is 1. If you look to this and that 1, you will find them that are identical, right? So pretty much I can come and say that, I have here A, B, and I XOR it with Cn. Then I take this A and B and Cn and I push it inside majority encoder, and here's the carrier. Then I take this pass and I do it with non-gate, then I'm done. So did you see the trick? This trick is important. Why is it important? Because I can come and tell you, can you please build me a circuit, whatever, you write the design using hardware description language, that's the circuit using majority encoders or whatever. So first of all, you have to have enough knowledge to play with the digital logic. Then you will design them as a submodule. Then you will build a top module, you instantiate all the pieces, you put it inside, everything will be connected. That makes sense? Is it clear, guys?
Yes, it's clear.
Super. So now, this specific majority one is just a majority of 5 inputs. So basically I have 5 inputs. I'm looking for the ones, and the higher number of ones basically will be taken to be the outputs, others will not be, right? So you will look at it, you will start picking the highest as I did before, and then, you will start describing the statement. So here, you're gonna have a bunch of what? And. So basically this code in front of you is not written using the structure modeling. This is written using what? Data flow. Data flow modeling. So I can be also very specified. I can just specify to you, say that, everybody has to write his code using data flow modeling. Or please describe the 5 input or 4 input majority bit encoders using the structure modeling or using the behavior modeling. When I say design, that means you're gonna write the code, you make the process of the test tables and everything, and then you will put the test bench. And as I mentioned, since you already have the luxury of opening the computers and run Vivado, you can even attach the waveform if you can. That makes sense? It's supposed to be clear. Now we're gonna do the same trick of the top V and put the switches and LED, call the right one, and then you will connect it to the test bench and so on. Another example, 2-bit comparators, for instance. If I would like to compare between A and B, what is the best way to do it? Everybody should remember from the 2300. And I can come and tell you, build the 2-bit comparators using a network of multiplexers. Then that's also, you need to look to your code and the documents we shared in the 2300 before. If you don't feel comfortable about it, I can repeat it. How many of you know the trick of using the multiplexer, for instance, to build 2-bit comparators? How many of you in favor? I forgot. No. So how many of you would like me to do it? Okay. That's one person. Not that many people would like to have it. Not that many. Okay, I'll do it. Just joking. Anyway, so okay, look at the following, right? So I have a 2-bit, right? So 2-bit, that means I have here B and have here A, right? So A1, A0, B1, B0, right? So I have a 4-bit. 4-bit, that means how many states I have? 16, right? 2 power 4 of inputs, so that means 16 states. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? So now how can you sort them? You already have 3 different outputs, right? You can have one of greater than the others. We have to design it to a certain step, which is maybe B greater than A, B greater than A, or B is equal A, or B is less than A. Right, which is, we call it here greater, equal, less. So those are the 3 possible outputs we can get out of the comparators, right? So then, you know, we have here 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Then 1, 2, 1, 1, 1, 2, 1, 1, 1, 2, 1, 1, 1, 2, 1, 1. Then, you know, we have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And then, you know, we have here 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? Now, we're gonna use colors here, you know? So colors, I love colors. So let's go into the first part, right? First part here, it's very straightforward. So I have 4 statements compared with 0. So this is 0. So what those statements is basically 0 compared to 0. So that means I'm in what? In equivalence or the greater or the less. So have you noticed I consider them as a 2-bit, but I return it back to decimal because, you know, at the end of this is 2-bit comparators, right? So it's gonna be E. So here we're gonna be E, and this 0, 0. Then 0 and 1. So that means here. 0 and 2 here. 0 and 3 there. Then, you know, the rest is gonna be 0, 0, 0. Right? Now we're gonna have a different set, which is 1, 2, 3, 4. Then I have here 1 with 0, so it should be greater. So gonna be here 1, 0, 0. 1 and 1, so gonna be 0, 1, 0. Then, you know, 1 and 2, so gonna be here 1, 0, 0. Then, you know, 1 and 3, so gonna be here 1, 0, 0. Then, you know, we're gonna back into the 3rd group, and the 3rd group is gonna be 1, 2, 3, 4, right? So you're gonna go here and say color. Okay, so basically you're gonna have, no, I'm sorry, you're gonna have color. So 2 is 0, greater. I'm sorry. 2 is 0, greater. 2 is 1, greater. 2 is 2, equivalent. 2 is 3, less. Then, you know, I have the last group, which is this guy. 1, 2, 3, 4. So basically 3 with 0, 3 with 0, so gonna be a 1, 0, 0. 3 with 2, 1, 0, 0. 3 with 1, I'm seeing 1, 1, 0, and here 1, 0, 0. 3 with 3, gonna be 0, 1, 0. So what we did now, we finished. Yeah, it should be 23 on that. It's actually even in the lab and in many places, you know, so don't worry, you know, you'll find it everywhere. So now, you know, we finished the first part, right? But, you know, what about the second part? You wanted to have with multiplexer, right? How can you do it with Sorry. You want it with multiplexers. How are you gonna do it with multiplexer? Somebody can tell me how can we do it with multiplexer?
So we could use the first two inputs from B as like a selection.
Yeah, or you can do it. What is the size of multiplexer should be actually? That's another question.
A 4 by, yeah.
Wait, can you say that again?
You make it 3/8. What about 3/8? The 8/1, I'm sorry.
8/1?
Yes, 8/1 multiplexer.
Yeah, that would work if we put the most significant bit, if we put it as the selector, because there's only one, like the first 8 are zeros and the second 8 are ones.
No, let me show you. 0, 1, 2, 3, 4, 5, 6, 7. Right? And here is that. Output will be just one output. So basically, this is going to be for G. So you're going to do it for E and L. You can make it also with 4. We can try everything. You know, I like to show people that everything will work. You know, so let me show you. Let me show you. There's fun. You know, there's a lot of fun here. First of all, what will happen? What will happen if I take the B0, A0, A1, A0 as a selector? What do you think? So I can make it like this. B0, A1, A0, and those guys will be the selector of the multiplexer. Then there is one which is the B1 we didn't take, right? Do you agree? B1 will be the input, exactly. But then, you know, we have to be a little bit tricky. Why a little bit tricky? Somebody tell me. Let me tell you how I'm going to be tricky. So how many B0, A1, A0 is equal 0, 0, 0? 2. Here. And there. Can you see the square I made? So in this two particular, we have B0, A1, A0 is equal to what? 0. Do you agree? Then I found that when this happened, the output is equal 0. But I found when this is happened, the output is equal what? 1. But here is this 0, 0, and here is 1, 1. So pretty much I can just write this what? B1. That makes sense? And actually Eduardo did it. So B1 will be the inputs, yes. So is it clear to everybody what I did? Hello, yes. Okay.
If we did it like that, can you make an example of?
I'm gonna continue the rest, right? So I did this one, let's move forward. I'm gonna make it even with different sizes, just wait. Now, the second one, right? Here, the second one. So 0, 0, 1, and 0, 0, 1. 0, 0, 1, 0, 0, 1, right? And when this one happened, that was 0, this is 0, right? And when this happened, that was 1 and 1, right? So pretty much that's also B1. Then, 0, 1, 0. 0, 1, 0. 0, 1, 0, here's 0. 0, 1, 0, this is also 0. So pretty much no matter what is the value of the B1 is, the output is 0. So they're going to be connected into the ground. The input. which is gonna be the output. So anyway, so now 0, 1, 1, 0, 1, 1. So 0, 1, 1, here is 0, 0, 0, 1, 1, here is 1, 0, so still connected to the ground. Then 1, 0, 0, 1, 0, 0, 1, 0, 0, that was 0, now is 1, that was 1.
Now it's 1.
That was 1, that's 1 still? Something is not correct. Is it?
No, it's correct.
So no matter what, it's gonna be 1. So we're gonna be connected to the VCC. Okay, now 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1 is gonna be 1, so gonna be B1. Then 1, 1, 0 was 1, 1, 0, right? 1, 1, 0, 0 here and 0 here. 1 here is gonna be 1, 1, so it's gonna be B1 as well. Then 1, 1, 1 is 0, 0, 1, 1, 1 is 0, 0, so it's gonna be at the end of the day connected to the ground. So what I did now, I built a multiplexers, taking the input as a B's, and then the controller gonna be B0 and A1 and A0. You're gonna do the same thing for the E and out. That makes sense? It's easy, right? If you wanted to make it with 4x1, then you have to be a little bit tricky because you can actually make a K-map for the rest, to combine the two others to go as an input to the specific input of the multiplexer. That makes sense? It should be easy. But don't make it difficult for yourself. What you can do, you can look at this and say 8, 16, 8, 32, 16, and so on, and it will be straightforward, unless I will trick you. Then maybe I can tell you build it with bunch of 2x1 multiplexer. In that case, what you're gonna do, you're gonna instantiate 2x multiplex, right? How can you instantiate the 2x multiplexer? We already have the instantiation we learned before. And the 2x multiplexer, in that case, you can have like 4 of them here connected to 2 of them connected to 1 here. So end of the day, you're gonna have an array of multiplexers, which is providing to 8x1. Make sense? Should be clear, right? Okay. Now let's go into the rational or the relational operations. So a relational operation that, if I want to work making this comparator thing using behavioral modeling. So I don't need any more what I did in front of you. Basically, I can just say, if it's greater than, do this. If it's less than, do this. If it's equal, like this. And then, you already build the equivalent.
So, Professor, when we're dealing with very high numbers of bits, like, for example, if we're doing 6 bits instead of 4, would you recommend doing K-map and then gates or multiplexers?
It depends on the question. So maybe I can say, make it behavioral modeling, make it say structure modeling. Maybe I can tell you, I will lead it for you so you can pick up by yourself. I'm not gonna make it a race in how can I make it complicate the stuff for you guys. The whole my questions is based on tricks, which is like you answer in like a half sentence. If you look at it, that's it. Okay, anyway, the greater thing in a perspective of the z and x and 0 and 1, the table already shared with you, so you can look at it, there's no problem. And also the equality, like, if you say equal, what does it mean? Not equal, and so on. And equal, not equal in terms of logical part, how it looked like. While I was talking, actually, that majority circuit, it was inside in the top, but somehow I grabbed this wrong slide. So basically, this belongs to the one in the top. So you have it in order with you. I already shared with you this patch of slides in the folder of the week 1. Can you look at it? You will find. Then the logical operation. So what you want to do is logical operation, like You want to do is like true or false, or ending the whole entire bus without making bitwise or XORing them and so on. So you will find it there.
Professor?
Also, yes.
Could you elaborate on the case equality?
Which one? This one?
Yeah, correct.
So the trace case equality, this is for logical. If you are comparing for logical, not for comparing with values. Like you're comparing something in logic, like in control unit, not in data bus. Data bus is number to number. But later on, in the course, while we're working, if you would like to build a processor, so the processor, normally you have a data bus, and then there is a control bus is controlling it. So the statement or syntax you will use for the control in terms of equality, it will be triple equal, not double equal. Okay, it's not clear now until you will have a crystal clear example in a control path.
Okay, thank you.
Anyway, shift, we talked before shift right, like shift left, shift right, rotate left, rotate right. All of those guys you can find in here already. Like, and also I mentioned, what is the difference between logical shift versus arithmetic shift? Any of you remember?
The logical shift just shifts
with zero.
Shifts it so that the most significant bit gets deleted, and then
you don't reserve the you don't reserve the most significant bit. Basically, you push with zero in any way. But the arithmetic shift, you push with the most significant to reserve the sign. That's the difference. Okay, look. Now there is some other stuff like concatenation, replications, and stuff like that. So if you would like to repeat something multiple times, you can concatenate it. You can replicate it, like the last symbol in front of you. Like you would like, let's say that you have a bus is 3-bit, which is written in at 9 or 5, right? You want to expand it instead of to be 3-bit, you would like to make it a 9-bit. So basically, you come and say that curly brackets 3, and then you put it that's what you would like to repeat it. At the end of the day, it will be replicated into 9-bit, and it's gonna be 5, 5, 5. Concatenate, like you already have something wire in A and wire in B, you would like to put it in C, and concatenation. One is the most significant, one less significant, and you put them in order and you concatenate. So that's basically what you have in concatenation. Conditional test, that's something I'm gonna tell you later on for building multiplexers, and which is a part of the data flow and concurrent state. Then there is something that's called operator procedure, or the preference or the appearance, basically. Which one it will be high priority than the other one. You know that, right? Do you remember in the math or C, when you say X plus Y time, and you would like to make a time of all of them, at the end of the day, you have to put them in a bracket and you say the time, then compiler will understand that you group this and you time it in something else, right? So that's basically the priority of them if they are combined together in one equation. Which one have the highest one, which one it has the lowest one. Okay? Then I told you a bunch of abstractions levels of the topology we learn, which is called abstractions of the hardware, like behavior model versus RTL model versus structure models versus the procedure blocks, and what the procedure blocks are. So I told you about the behavior models and so on, but I told you, I used the initial block in front of you, but I didn't tell you that's a part of something that's called procedural blocks. That's just like theoretical thing. So the procedure blocks, it's a kind of behavior modeling code, which is helping you to define a certain rule in a certain block. That block will do this certain rule, and the other blocks will do something else. So you have two different things. One is called initial and one is called always. The initial, we already use it in front of you in a test bench, and it's basically in a time 0, the whole entire thing will be processed and it will stop. That means there is no looping back. While the always block is always. That means some statement or some list of sensitivity lists will be present And then if some changes happen in this list, this procedure will be completely what? Updated. And it's called always block. Example, I showed you about the initial block, while into the always block. This is the always block, basically is describing the sequential circuit. So you guys remember in sequential circuit, what elements we learn in sequential circuit in 2300? We learn latch, right? And then from latches, we build the flip-flops. And then, we learn the excitation table, the truth tables, and characteristic tables of the flip-flops. Do you remember that? And we said the clock based on the edge of the clock, which is the event. So you have two events of the clock. You have positive edge versus the negative edge of the clock. How many of you remember this? It's no shame to say I don't remember. That's fine.
Remember.
Okay. So in that case, that if you notice when I said always block, that means that certain rules will happen in between of this block. And in that case in front of you, when I said module, example, whatever, this is an example of the D flip-flop. Why? Because in every single positive edge of the clock, the process will check whether the reset is high or not. If the reset high, that means the data will be equal 0. If not, and the enable is high, the input will equal the output. That's basically what is the translation of written in front of you in always block. Let me make it bigger for you. Everybody can see it, right? So, and since it's a flip-flop or sequential circuit, I'm not using wire. I'm using register, as Mario and Danash. He mentioned when I made a mistake about the wire of the input and output. That makes sense? So if anybody look at this, they will come and say, oh, it's always block, sensitivity list, it has a positive edge of the clock. That means this is sequential circuit. That's the first thing. The second thing said that, every single positive edge of the clock. Yeah, so that's what I want to say. So how many of you attended with me 2300?
I did.
Just two people didn't attend with me. Okay, that's fine. It's not the end of the world. Let's do it again. That's fine. Okay. There is two different resets. One is called asynchronous reset, and one is called a synchronous reset. How many of you heard about this? Synchronous reset, asynchronous reset. Okay, synchronous reset, this is what we have now. So basically, the reset with the positive edge, they have to happen together in order to make data equal 0. So that's called synchronous reset. Asynchronous reset, it doesn't matter where exactly I'm at in the clock stage, I will reset. Let's say that, I'm in high of the clock, I'm in the low of the clock, I'm in the positive edge of the clock, I'm in negative edge of the clock, I'm in nowhere of the clock, but then, reset happens, automatically data will equal 0. That's called asynchronous reset. That makes sense? While synchronous, you are tied by a bunch of conditions. And the conditions we have, one second, because this thing is not crazy. The condition we have in this case, positive edge of the clock happen, while the reset at the same time is high, then data will equal 0. If not, if enable happen while the positive edge of the clock happening, the input will equal that. Make sense? Kind of, yes. In the software, yes. So if you would like to compare here, initial block execution start at time 0. So when the time start, initial will start and finish. Always block execution also start by 0, but then it will start looking to the changes into the sensitivity list. Then the sensitivity list, it's basically the list written into the brackets after the @ sign of the always. So let's say always block can be used for actually describing combinational circuit and behavioral model also it can be used for describing a sequential circuit. How? If you remove the positive edge of the clock, and for instance, you put enable, so always at enable, so that means now I'm no longer sequential, I'm actually what? Combinational circuit, looking after the changes in the enable. That makes sense? And that's basically what we have. So the, some writing up here, procedural assignment statement, assign values to register, integer, real number. And you know what does real number mean, right? Real, that means integer with fraction. Or time variable, and cannot assign value to the net. That means I cannot assign value to wire, because you don't have a way to hammer the wire and push force value in it. The only way to do it, you have to do it force and release, which is not here in the test bench. It's just for testing, not for synthesizing. You can assign to a register, which is a reg data type, the value of the net wire as constant, another register of specific values. Examples, I mentioned to you many times of the examples here, and what is the bad procedure assignment versus the good procedure example. So look at it very well. You will find what is the good and what is the bad. Okay. Now, the question that I think one of you asked me about the risk condition. Who asked me about the risk condition? One of you. I forgot. Go ahead. One of you asked me, right? The risk condition. So, since we have always block, and it can be used for sequential, and it can be used for sequential, and it can be used for combinational. So we need to learn there is two different ways of representing the input. I think yes, here is the one actually. So in that case, we have something that's called blocking assignment versus non-blocking assignment. This is very, very important. It's a very important subject. It's one of the most important subjects we have. Even it does look like really silly, but it's not really silly. So if you want to infer combinational logic with an always block, use blocking. If you want to do it for combinational circuit, use blocking. Why blocking? Because at the end of the day, we'll come and tell you exactly at this time this will happen. You know what I mean? Again, so blocking is allowing you on catching time because you don't have a clock. So you are actually tied by the response time of the gate itself. So in that case, everything is already pre-calculated. While non-blocking is completely great for the sequential circuit for avoiding the race conditions, as your colleague asked. So non-blocking is completely important for the sequential circuit. Somebody can ask me, Professor, is it possible to use the blocking in the sequential? I did before, but that was really critical and I needed for a specific critical mission. It was for very, 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 very important thing. When I was building a bioinformatic processor for University of Illinois for accelerating human DNA. Yeah, so basically the non-blocking is a parallelism, while no non-blocking is not parallelism, it's non-blocking as sequentially. So you already have everything sequential to everyone. So the blocking, the one, with combination, everything is basically parallel. So blocking are executed in order they are coded, hence they are sequential. I'm sorry, you're right. The blocking is sequential since, the non-blocking is gonna be the parallel one, okay? So be careful because you can cause yourself to be in a race condition in a way that, two different things, they have to report at the same time and there is dependencies can actually cause hazard. And the hazard means that, you are expecting the output to be written in a certain location and you will find the output will be a don't care or the Z, which is high impedance represented on the waveform. We're gonna do a lot of examples, but this slide is very important. It's very, very important. It's very important. Again, it's very completely important. You have to look at it, please, completely. So what I'm gonna do now as a last part of this lecture is going to be parameter. I'm gonna use a parameter in front of you, and from there, we're gonna stop. Anybody has any questions so far? Any question? Any answer? Anything? You guys still there? Hello?
Hello.
Yes, good.
I have no questions.
Super. Now I just want to be sure nobody's asleep or something, So now we are closing this to start doing some tricks, right? So what is the trick? So I'm gonna say here, a project, add a project, new project, next.
We can't see
Cheers.
your.
You
screen.
cannot see, oh, sorry, I forgot. That's a very good thing that, I ask you. That's why I said, are you guys asleep or still awake, Can you guys see now?
Yeah.
Okay, so the project name here, let's call it, what should we call it? Parameter. Project. RTL XC7 A100 TCS -1. Finish. Yes. Now at source, create constraints, right? Create, and I'm gonna call this what next? You can name it after the project, that's fine. But I just like to use it in Nexus project. I have 31. How does it happen? So CBP, right? Not CBP, then Google. Nexus for XDC. GitHub. And then I go here, I already create the Nexus, then I just put it here. Okay, now I will just go ahead and say add source, design, and create a design. I won't think about what should I create for you guys. Let's make multiplexer 4x1, okay, with data. So we're gonna call it max 2x1 first. So I can apply some stuff we learned today, okay? And then I say finish. Now I'm gonna do something new. I haven't showed you this before, right? So the multiplexer, we're gonna have select, and it's gonna have A as an input, B as an input, and then AB and AB, maybe, and then I can have output. Not gonna be output. because I like to follow my notation, no matter that, you know, it's acceptable or not, I'll just say haywire. Then I can go back here and stay with me 1 second. And then, you know, from there, I can just say here, assign OB is equal what? We're gonna make it like this, not select ended with a or with select ended with B. So can you guys see what I did? What I did now, I described by using one line, the multiplexers using what? Using the data flow here. I can make here data flow. Be sure while you're designing, you put here your name or the name of the group, you put all of your group names, and then, you know, put here the project name, what is the project about, the target of the device, which is XC7A100TCSG, blah, 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 whatever, 2 something, something -1. Then tool version here is Vivado 218 point, I don't know, 2. Description, this is a multiplexer. We are building data. And then dependence is like, you know, is there any other files you're gonna call or instantiate and so on. Okay. Now we build one multiplexer, right? So we need to make, we need to make the parameter, right? So in that case, I can just go ahead and say add, create also another design. And I said here, multiplexer 2x1, and then, you know, here, data. And then I will go there, I finish. And from there, I can come and say that, you know, I need the input 1, input 2, select, and then, you know, output. And we're gonna make it what? Like that. Okay, now we need to take this. Everybody's following me, right? Hello?
Yeah.
Okay, so now we're gonna be like this. And we have to have haywire. And I'm gonna instantiate this guy, so I'm gonna put it in front of me for a while, and I just call it what? mux2x1, and I open like this. And I'm gonna be dot select dot a dot b dot so b. And then from there I can take this. And then here I will say size minus 1, size minus 1. But we don't have size, right? So what we can do here, we can just go ahead and say parameter size. So did you see what happened now? I make it the parameter and I set 4. So they're going to be 4 minus 1, 4 minus 1, 4 minus 1. That makes sense? Now select is going to be select. But this also has to be unity. So I would say multiplexer unit, let's say U0, which is standing for the bit number 0 in the multiplexer, right? So I can go like this. That's not smart, but anyway. Okay, and then I go here and say select, select. By the way, when you do like this and you keep those are empty, they're considered floating. So that means the compiler will what? Optimize them later. They're gonna remove them. You know what I mean? So you have to be careful if you don't need any certain output or so in one time while you're designing, you can just keep it input like empty like this, and automatically it will be optimized. And that's unit 1. Later, I will show you another trick using for loop, which is gonna make everything completely optimized. But I'm just giving an example. It's gonna be unit 2.
So, Professor?
Yes.
You have to make that design mux2by1_data when you want to make multiple multiplexers, right?
Yeah, I'm gonna show you now. Just give me a time. So now gonna be here what A 0, B 0, C 0. No, not C, it was OP, right? Okay. I'm sorry. Not A, it's input 1, right? Input 2. Makes sense? Now we're gonna do the same thing here, input. I could just do it, that's my mistake. 2, and then zero, 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 here, 1, 1, 2, 2, 3. I'm gonna make another example, so that will be more interesting because it will be more dynamic. So what you have in front of you now, I decided size to be 4, right? Did you see what happened? I decided 4 to be there, right? And then 4 is representing to be size minus 1, so it's gonna be 3.
Around that time, I'll go.
That makes sense? And from there, I can just go ahead and make a test bench. I will find that, value is written from the inputs and it will be selected. You know what I mean? This is a parameter, right? Later on, if I have a kind of mechanism making this to be a generic, like for instance, let me actually make you an example of this. 1 second. 1 second. I will make it for you now more generic. but that will be different, okay? So if I go ahead like this and say here, look at this, this is really fun. So I would say gen var I, okay? Then I will come and say generate, and then I make a for loop, and I equal 0 to I less than size, okay? Comma I plus plus. Then I say here begin, and there I will say end. I don't like C. Let's say I equal I. Okay.
So that loop is creating the multiplexers for you there, or?
Just wait. I don't know what's the error now. There's an error now. I don't know why there's an error. That's +1. Okay, that makes sense. Okay, so I can actually comment out those, right? So I can click here and say toggle line comment, which is like this. So I don't need those anymore, right? Then I will remove every I here is 0 and I put I. What will happen? And I make this one like this, remove that 0 and I keep it like that. Why there's an error here? Consider an error here. Wait. It's supposed to be like that, so oh, I'm sorry, it has to be in generate, I forgot. Now it should be perfectly fine. Look what happened in the side. Can you see it? Hello?
Yes.
Can you see what happened? Four of them go there. Look, wait. Let's see it like this. What happened? Can you see it?
Yeah.
Which is fun, right? Now, this is the parameter, right? If I call this into, if I call it into an instantiation environment, right? I can change in the environment, even there, here I wrote 16. You understand what I'm saying? So I can go ahead like this and just say design a new thing, which I call it whatever, you know, let's say create design. And in the create design, I will just say, custom multiplexer, just an example, a name, you know what I mean? And from there I say finish. And here I can just go ahead and say also input, output, whatever, right? So it's gonna be here, let's call it int and and a and B select, and then I say here OB as an output. Now I just do it like this, and I keep it forward, okay? Then I say connect, and I will take this guy completely with me there, just like, you know, to remember the order, okay? Okay, now I will write here mux 2x1 data, right? And then I want to call it with something which is u expand, and then I will say here size equal 16 something. Then I will go ahead and do like this. That will be fixed momentum. Anyway, so now gonna be dot mb1 dot mb2 dot select dot ob. Okay, now I can just go here and make another parameter, and I can size custom, and I will give it any number. Let's say 52. Okay. Then I will go ahead and say size custom here. -1, -1, -1, right? I don't need this anymore. And that will be here custom. What is the error here? Undeclared. Did I write it like upper letter or lower letter? It has to be dots. And it has to be like this. Now inputs are gonna be inputs in the select and I can move this like what do you mean by unknown time? Oh, sorry. Everybody can see what I'm doing or not?
Yes.
Yes. So what I did now, before the max data, right? It was what written there, what 16, right? Let's make it written 1, just like 2, you know, like this, right? Then I call it there, and I instead of 2, now it's 32. That makes sense? What you're gonna have, what you're gonna expect here, you're gonna have these 32. Look, 32. That's called what? That's called parameter, because you know the parameter is what you can overwrite in the level of an instantiation. Local parameter is not. So for instance, you know, if I change this one, I make it local parameter, like local, like this. That was the name, right? Let me see to be sure. It was called local, right? Local param, I'm sorry. It's called local param. So now it's local parameter, right? But when you go into the custom, Look what happened. Huh? 32 didn't do anything. You return it back to 2. What does it mean? It's completely what wired or hardwired. So my question now, do you guys understand what is the difference between local parameter compared to parameter?
Yes.
Just one person. I want to hear the rest of the people.
And the local parameter can't be.
Yeah, I want to hear the rest of the people, not just 1 or 2. I want, yes, Yes, exactly. So parameter will, look, max multiplexer 2xd, whatever, right? Here, if I completely remove it and I write parameter, even this is in 2, right? But there, this one is 32. Automatically, it's remapped itself to 32. But if I remove the one in the beginning and I make it local param, like this, no matter what I did there, and I make 32, automatically still me, you know what? It's not 32, it's 2.
Wait, Professor?
Yes.
What does the pound symbol do when you have more parameter?
Which one?
The pound symbol?
This one?
The one you have before parameter. You said pound and then parameter, yeah. What does that do?
Oh, this is the way how to write parameter.
Oh, I see.
So the way you write parameter is basically you have to put this the hash thing, right? And then you will put the parentheses, and then you will put whether it's gonna be local or what's gonna be parameter, right? Then you will say what is the parameter is, and the value of it. Then you will start after that, if you want to make a parameter inside the module. By the way, you can actually remove it from there and you can put it under the input output ports. But in that case, input output port, it has to be what? Pre-calculated already. You understand what I'm saying? So for instance, if I go ahead and take this like this and I put it there, it is no longer figuring out this. So this is basically sequential, if you notice, right? Because it's say error, because it doesn't see, if you stop there, it will tell you what is size. I have no idea what is size. You know what I mean?
So do you use it for delay as well? I think I remember seeing it.
You can do it for delay, but don't forget, you cannot make delay in the synthesis.
Oh.
That's basically what you're talking about. It's a simulation.
Oh, I see. Okay.
Oh, that simulation you're talking about. Wait, I'll show you. I know what you're talking about. It's not here. Maybe I can close this project. Later on, we can make a test bench next time. But I can open there and I see what you're talking about. This bench here. That's what you're talking about, right?
Yeah, that's what I was talking
about. Yeah, so delay, it's this, but also this one is also defining number in system. So that's why, you make it the hash thing, and then, parentheses, you put whether they're going to be parameter, local parameter, and then from there you say the name of the parameter you are actually going to use and equal what, and then, you will start using it. When you go instantiating, if you go back into the code here, close the project, open that project. That was the thing, right? So you said here parameter in the beginning because everything depends on the size. So you put it in the beginning of the module, right? And here, look the different color here, right? Then, since you already defined it, you can use it in the text. And I use the for gen, I will describe to you what is the difference between for loop compared to the for generate in the following weeks. But, at least I just wanted to show you how can you make everything dynamic. Okay, look.
Professor?
Huh?
I had a quick question. Back when you were instantiating using a for loop,
yes,
I noticed that every single instance, instead of rewriting over the same space, it would simply just save it as a new instance. Is there any way where we can make it rewrite over a previous instance?
What do you mean, like, changing the names?
Exactly, yeah.
No, because the for loop is actually auto-generated. So if you want to change the name, you have to make it manual.
No, not the name. If I want, instead of it creating a new instance on the, I wanted to rewrite a previous instance. Can that be done?
Instead of the multiplexer like this, you can just go write it inside basically. What are you talking about?
So you know how when you have it, like the size is 32, it creates 32 different instances, correct?
Correct.
Instead of it creating a new instance, can I have it overwrite a previous one?
No. The other one that you know, it's already there. Nobody can touch. It's already there. So what happens? Actually, you call it. You replicate it. You get a like a, you know. Do you remember? Have you take data structure? So
Yeah.
basically, you know, if you do this, you know, you have the child and the parents, right? The parents still exist. So the child will take some genes from the parents, and then you know it propagate, right? So I cannot kill the parents or completely change the parents. I have to get the child, which is now you know the instantiation, and then I expand and contract, expand, and extend, and stuff like that. The child itself.
Okay.
Except,
and then another question I had is when you were using your local parameter,
yes, sir.
is the scope of the local parameter restricted to the module itself or within the file?
It's a module itself.
Module. Okay, thank you.
Yeah. Any other question, guys, before we finish? Any other question? Any concern? Any problem?
Make sure this the lecture has been recorded and is going to be uploaded on Blackboard, right?
Of course. I'm gonna put a copy in the 3300 lab and a copy in the lecture in the 3300.
Sure,
Any
yeah.
other question, guys?
Professor, when I simulate my test bench and ask for the number of jobs, what does that mean?
Ask what?
It asks for the number of jobs?
Yeah, number of jobs,
What
the
is that?
number of cores. So you can come and say any big numbers. So what numbers you already have? I think you have up to 8.
Okay, so the more jobs I put in, the faster, right?
That means the cores will run fast and process.
Okay, that makes sense.
Oh yeah, Eduardo, you downloaded the new one, right?
Yeah, it works now. It works. I tried it with my.
It wasn't a license, by the way.
Yeah, it wasn't. It was something else.
Yeah, I think it's some dependencies in the software because you're using Windows. I hate Windows.
Yeah.
It's better. If we have time, I can tell you also the tricks of Linux. You know, so you will be able to work really hard on the how to description language using Linux. And by the way, Linux also can help you with C. If you are really programming with C, you don't need to go Visual Studio and all these things. There is something it's called GCC compiler. GCC. Have you guys heard about it? It's called GCC compiler. Yes, you guys say GCC compiler and you put the name of the file, you click, everything will come out. Okay, since you guys don't have any questions, I assume that you know everything was really clear today. So I will let you guys go take some rest and enjoy the rest of the week and even enjoy the rest of the day. Don't hesitate to contact me if you have any questions. A copy of this recorded video will be posted on the Blackboard and we will move forward with the stuff soon.
Actually, Professor, can we have the meeting for like maybe 3 more minutes so we can exchange information for the groups?
Yeah, go ahead. But you already have the Slack.
Oh yeah. Well, it's like a preference on how you wish
guys
to.
Don't like the Slack. No, that's not really nice. Slack is used by like IBM, Intel, stuff like that. You know, I'm trying to put you in a professional way. If you want. You guys go ahead. Go ahead. I'm not gonna close the door. Still have time.
Any example projects posted anywhere? Just for Vivado.
The Vivado, what happened? Oh, sorry, that's email from the news. What?
Do you have any example projects posted anywhere?
I mean, everything is recorded, right? If you just go ahead and put the recording aside and start writing, if I give you everything easy, that will be easy. But if you write by your hand, you will make mistake, right?
Mm-hmm.
And when you make mistake, you will learn. Do you agree?
Yeah.
So if I'm you, you know, one screen, you put this recorded thing, mute my voice, there is no problem. And you know, the other side, you just open the Vivado and just copy and see if it works. Then next time, try to trick yourself with another challenge without looking to the video. Then okay, perfectly fine, looks super. Then I learned the tricks. That's it.
All right, thanks, Professor.
Thank you. So all the best, guys. So I can close now, right?
Yeah, now it's fine.
Okay. Thank you. Have a wonderful day. Thank you. God bless you. Stay safe. Bye.
Thank you.
Professor.
Thank you, Professor.
Thank you.
Well, Professor, I have one quick question. Does everybody in the group have to have a board, or just one? At least one is okay.
Huh?
Oh, I'm sorry. So does everybody in the group have to have a board, or is it just one person?
It should everybody has a board, because you have to also do the stuff by your hand.
Gotcha.
Is it possible to borrow a board?
You can borrow boards, of course, yeah.
From you though, because you said during the semester that
the problem I talked to the university. There is no way for people to be on campus.
Yeah.
Unfortunately, even myself, I take permissions.
Yeah.
Okay.
This COVID is really.
Thank you, Professor.
Okay, thank you. Have a good one. Thank you. God bless you guys. Bye bye.